Hi, it's Mr. Duffy. In this video, I'm going to show you how to calculate the energy of a wave. And you'll use this information to help you on the next couple problems in the worksheet. So in an energy of a wave problem, we're going to use this equation, E equals h nu, or sometimes again, nu can be represented with the letter F for frequency. So either way you represent it, it's still going to be the same thing. So E is your energy. H is a constant. It's always going to be 6.626 times 10 to the negative 34th. That's called Planck's constant. He's the guy that kind of made this equation, times the frequency. So the energy of a wave depends on the frequency, basically. Okay, so let's take a look at a problem. It says a certain photon of light has a wavelength of 422 nanometers. What is the energy of the light wave? So again, um, all photons contain energy, and again, different wavelengths, different frequencies contain different amounts of energy. So we just want to figure out how much energy is in this photon. The first thing is, though, it doesn't give us the frequency. So if we want to plug it into our last equation, E equals h nu, well, we don't have the frequency, so we can't really do that. What we actually have to use is the equation from before, and you'll see this in some of your other problems. The speed of light equals the wavelength times the frequency. So we have to find the frequency first and then plug it into the energy equation. So let's do that. C is the speed of light. That equals 3 times 10 to the 8th meters per second. The wavelength is given to us in the problem. That's 422 nanometers. But basically what I would need to do is move it over to get it. I need to get it into meters. And so 422 nanometers becomes 1, 2, 3, 4, 5, 6, 7, 8, 9 spots over, becomes 0.000000422. Um, okay, so again, just moved it into meters. So that's what I would plug in into my equation to solve for frequency. And again, basically after I do that, I can just type it in my calculator. 3 times 10 to the 8th divided by 0.000000422, and I get a frequency of 7.11 times 10 to the 14th. That would be hertz. The units for frequency is hertz. Now that is not the answer to the question, that is just the frequency. And now I would plug it into my energy equation. So energy equals Planck's constant, 6.626 times 10 to the negative 34th joule seconds times what I got from my last problem, 7.11 times 10 to the 14th hertz. Okay, and that'll get my energy. 6.626 times 10 to the negative 34th. And that comes out to be an energy of 4.7 times 10 to the negative 19th joules. It's a small amount of energy, but that's just for one photon, and you got to think you got trillions upon trillions of photons if that's the case, and so it adds up to be a lot of energy. Okay, this is how we would do an energy of a photon problem. Thank you for watching.